Statistical definition of entropy. We have previously said that all isolated systems eventually reach a state of equilibrium. But why is this? Why do they always reach equilibrium? We had also shown that the internal energy is a function of the properties of the molecules in a system. Can we also define the entropy of the system in a similar way based on the properties of the molecules? We have here a cylinder which is separated into two parts by a partition. The left half of the cylinder contains a gas, and it has a pressure gauge attached to that which shows a pressure of some arbitrary units of 2. The right-hand side has a vacuum, and the pressure in that is 0. The partition is now removed, and the gas spreads and fills the whole cylinder. The pressure on both sides is now the same, and the gas is in a state of equilibrium. But if the gas consists of randomly moving molecules, why is it that the pressure always becomes uniform on both sides? Why do we never see a stage where the pressure on the left would be different from the pressure on the right? To try and understand that, let's look at a simulation of this. Over here, we have a simulation in which we have 100 molecules which are on the left-hand side of this container. The slider at the bottom over here shows the position of the center of mass of these gas molecules. We now remove the partition, and the molecules spread out and they fill the entire cylinder. The slider is now moving to the center, and we can see that the number of molecules on both sides is very close to 50. To try and understand why the molecules distribute themselves so uniformly, let's consider a very simple system which has only 2 particles in it. In this, there are 2 molecules, one blue and one red. Let us look at how many ways we can distribute these 2 molecules in the 2 compartments inside this cylinder. First, we could have both on the left. In this case, the pressure on the left-hand side would be 2. The pressure on the right is 0. We could also put one of the molecules on either side. Now, there are 2 different ways we can do this. You could have either the blue on the left or the red on the left. In these 2 arrangements, the pressure on both sides is 1. Finally, we could put both of the molecules on the right-hand side. In this case, the pressure on the left is 0, the pressure on the right is 2. Now, if we want to describe these different arrangements, there are 2 different ways we can do that. The first is what is known as the microstate. In this, we are listing the possible arrangement of each particle. So, for the first arrangement, we would say that the blue molecule is on the left, so we'll denote that by L. The right is on the left, so that would be another L. The other arrangements would be denoted variously as LR, RL, or RR. So there are 4 possible microstates: LL, LR, RL, RR. The total number of microstates will be denoted by the capital Greek letter omega, and so omega is equal to 4. Now there's a second way to describe this, and this is what is known as the macrostate. So a macrostate is described by a list of properties that can be measured macroscopically. Pressure, temperature, mass are all macroscopic properties. In this example, we are measuring the pressures. So there could be 3 possible macrostates, where we have PL equal to 2, PR is equal to 0, PL is equal to 1, and PR is equal to 1. PL is equal to 0 and PR is equal to 2. So note that we have 4 microstates, but we have only 3 macrostates, because one of the macrostates, PL is equal to 1, PR is equal to 1, has 2 microstates that correspond to it. So let us list all of this information in a table. And we have 2 columns over here. In the first, we list the microstate, and the second, we list the corresponding macrostate. So for LL, we have PL is equal to 2, PR is equal to 0. Now for the 2 microstates, LR and RL, there's only one macrostate, PL is equal to 1, PR is equal to 1. And finally for RR, we have PL is equal to 0, PR is equal to 2. Let's add another column which lists the number of microstates. So that will be 1, 2, 1. And omega total is going to be 4. Now we want to calculate the probability of each macrostate. So we are going to look at the number of microstates corresponding to each macrostate and dividing it by the total number of microstates. So the column lists omega divided by omega total, and those would be 0.25, 0.5, and 0.25. The maximum probability is 0.5. And so we can see that there's a greater probability that we will have the particles distributed with 1 in each of the different compartments, and that the highest probability macrostate is one where the pressure is the same on both sides. Finally, let's divide each probability value by the maximum probability, 0.5. And we will use this last column to compare different systems with different number of particles. Next, let's look at a slightly more complicated system, which has 4 particles. Over here, we could have a larger number of microstates. So the first microstate we could have is all 4 on the left, and there is one macrostate where PL is now equal to 4 and PR is equal to 0. The second macrostate we can have is with PL equal to 3 and PR is equal to 1, and there are 4 microstates because we have to select 3 of the molecules to be on the left and 1 on the right. We could have PL equal to 2 and PR equal to 2, and there are now 6 microstates which correspond to this. PL is equal to 1, PR equal to 3, has 4 microstates. And finally, PL is equal to 0, PR equal to 4, has only 1 microstate. Let's add a column listing the number of microstates. The total number of microstates in this case is equal to 16. Finally, let's calculate the probability by dividing omega by omega total. And we'll see that the highest probability, again, is in the middle, where PL is equal to 2, PR is equal to 2. And finally, a column giving the probability divided by the maximum probability. Now we could carry on doing this, but it's going to become tedious with larger number of particles to actually write down every arrangement. So let's see if we can generalize this. First, how do we calculate the total number of microstates for a given number of particles? Now there are 2 locations for each particle. It could be either on the left or the right. So if we have n particles, for each one of them, you could put it either left or right. So n particles can be arranged in 2 to the power n ways. So for a system of n particles, the total number of microstates is going to be 2 to the power n. Now let's see how to calculate the number of microstates for every macrostate. Suppose we have a system with n particles. NL denotes the number of particles on the left, nr, which would be n minus nl, is the number of particles on the right. So omega nl would denote the number of microstates with nl particles on the left. So omega 0 would mean that we have 0 particles. All of the n particles are on the right-hand side, and there's only one way to do this. So omega 0 is equal to 1. Omega 1 means we have to select one of the n particles and put it on the left. The remainder would stay on the right. So there are n ways to do this. So omega 2 means we have to select 2 particles. So the first one we can select in n ways. The second we can select in n minus 1 ways. But we have double counted the total number of microstates. Because if we select, say, first the blue and then the red, or we had selected first the red and then the blue, we are counting those as different microstates, but they would actually become the same. So we would divide that by 2. Omega 3, now we can carry on in the same way. So the first one we can do it n. The second one is n minus 1, but we divide by 2 to avoid double counting. The third one would be n minus 2 ways, and we divide by 3 to avoid triple counting. And so for any number of particles nl, omega nl would be n into n minus 1 all the way up to n minus nl plus 1. And we divide it by nl times nl minus 1 and so on until 1. If we want to write this in a compact fashion, it would be n factorial divided by nl factorial times nr factorial. Now we know how to calculate omega for any number of particles. We can now plot a probability distribution. So we are plotting the probability divided by the maximum probability. So all of the distributions will peak at a value of 1. And we are plotting this as the percentage of particles on the left side of the container. So here we are plotted the distribution we had calculated for 4 particles. If we increase the number of particles to 10, this is what the distribution looks like. And this is the distribution for 50 particles. Now we can see that as the number of particles increases, the distribution is getting narrower and narrower. The probability is decreasing towards the extreme edges of the distribution. To try and understand why this happens, let's look at the case where we have all the particles on one side of the container. So what is the probability of having 0 particles on the left? The total number of microstates, omega total, is equal to 2 to the power n. Now only one microstate has 0 particles on the left, so omega 0 is equal to 1. So the probability of getting 0 particles on the left is equal to omega 0 divided by omega total, which is 1 upon 2 to the power n. Now we had calculated that if we have 4 particles, the probability is 1 upon 16. But as n increases, this probability decreases. If n is equal to 10, the probability would be 0.001. What if the number of particles is truly large, an Avogadro's number? In that case, the probability is so small that we cannot even calculate it using an ordinary calculator. So if we go to a very large number of particles, 10 to the power 23, the distribution looks like this. We can say with absolute certainty that the distribution would be 50% of the particles on the left and 50% of the particles on the right. So if we go back to our table where we had 4 particles, then we can say that the equilibrium macrostate is the most probable one. So that would be the one with the largest number of microstates. And so let's call that omega equilibrium. So for 4 particles, omega equilibrium would be 6, so omega total would be 16. So the probability is that we would see it in a state where we have half the particles on the left and half the particles on the right. So based on this information about the distribution of particles, can we define a value of entropy S that we can use to determine when equilibrium is reached? From the second law, we know that when S is maximum, the system is at equilibrium. And we have just shown that when omega is maximum, the system is at equilibrium. The obvious conclusion seems to be that we should select S as being equal to omega. So using this definition, let us try and identify the equilibrium state. So here we have a system which has 6 particles in it. So if we have a system where we have 0 particles on the left, S would be omega 0, so S would be equal to 1. With 1 particle on the left, S would be 6. With 2 particles, S would be 15. And with 3 particles, S is equal to 20. Now the distribution is going to be symmetric if we have a larger number of particles on the left. So we can identify that the maximum value of S would be where we have 3 particles on either side. And this is what we would expect to be the equilibrium state. Now with a small number of particles, this is probable, but we will see lots of occasions where we don't have an equal distribution. However, if we have a very large number of particles, then we know that the distribution is going to be such that all the microstates correspond to this equilibrium state. So omega equilibrium will be equal to omega total. And we can drop the subscript and we just put that as omega. So all the microstates correspond to the equilibrium state. For a system of n particles in a box, then we don't need to calculate the different number of microstates. We simply say that at equilibrium, S will be equal to omega, and this would be the value of omega total, which is equal to 2 to the power n. It seems that we have found a definition of entropy which allows us to predict when equilibrium is reached. But there's one more requirement we have to satisfy, which is that entropy is an extensive property. So let us test whether this definition is that of an extensive property. So here we have 2 systems, A and B, and they each have n particles. Both the systems are identical. So the equilibrium entropy, SA, would be 2 to the power n, and SB would also be 2 to the power n. Now if we combine them and we call that a system C, then for S to be an extensive property, the entropy of C must be equal to the sum of the entropy of A plus the entropy of B. So system C has 2 to the power n particles, so SC would be equal to 2 to the power 2n. But this doesn't work. 2 to the power 2n is not equal to 2 to the power n plus 2 to the power n. However, if we define S as being the natural logarithm of omega, then SA is equal to SB would be ln of 2 to the power n. And this would be n times ln of 2. SC would be ln 2 to the power 2n, which would be just 2n ln of 2. So SC is equal to SA plus SB, and therefore S is an extensive property. So this seems to be a much more workable definition. So now we can give a statistical definition of entropy. S is equal to K ln of omega. K is the Boltzmann constant and it has a value of 1.38 into 10 to the power minus 23 joules per Kelvin. And this was required because when Boltzmann gave this definition, there was already existing a definition of entropy, which was based on entropy being equal to the heat transfer divided by the temperature. And therefore, it already had units and a magnitude. And to make the two definitions the same, this constant K had to be introduced. Based on this definition, we can now try and understand the second law of thermodynamics. So going back to our initial system, where half of this is filled with gas and the other half is a vacuum, when we remove the partition, the gas fills the entire container and we have a state of equilibrium. Now let's try and understand this in terms of our statistical definition of entropy. So the initial number of microstates, which corresponds to the gas occupying only half the container, is omega I. The final number of macrostates, which corresponds to the gas filling the entire container, is omega F. If S is equal to K ln of omega, then the change in entropy during this process is K ln of omega F minus K ln of omega I. So we can write delta S as being K ln of omega F divided by omega I. But we know that omega F is much, much greater than omega I, which means that delta S is positive. So this is what we mean when we say that the entropy increases in an isolated system. It increases because the system grows from a less probable state to a much more probable state. The second law of thermodynamics is therefore simply because of the operation of the laws of probability. To summarize, a microstate is a list of possible arrangements of each particle in a system. A macrostate is a list of properties that can be measured macroscopically. The equilibrium macrostate is the one with the larger number of microstates. For a large number of particles, the equilibrium microstate is equal to the total number of microstates. The statistical definition of entropy is S is equal to K ln of omega. The entropy increases as an isolated system goes from a less probable state to a more probable state. At equilibrium, it is in the most probable state, so the entropy is maximum and it remains constant at that value.